My name is Boros, and I'm here today to tell you about FoundationDB. And FoundationDB is an open source database, which is very much like the Black Knight from Monty Python and the Holy Grail. Are you familiar with the Black Knight from Monty Python and the So it's similarly resilient, despite if you cut everything off, it still keeps going, and it gets up and goes on and bites your leg off. So about me a bit, I'm one of the founding engineers at Tigris Data. My background is platform engineering and running databases, and I'm very performance-minded. So I'm an SRE or DBRE, how they call it, who runs the production databases, typically hundreds and thousands. I mostly dealt with MySQL, but I had my fair share of other things as well. So I'm coming from the trenches, I'm coming from production, and this is me sharing how do we run FoundationDB in production and why is it it's a little known open source database, but very much undeservedly so. And about Tigris, we are an S3 compatible object storage provider with global buckets, so the data is always close to the user. So just so you know, to put all this in context, so we are sharing our experiences in terms of using FoundationDB as the metadata storage for an object storage service. And we are a relatively young company, but already have thousands of buckets and storing tens of petabytes of data and serving billions of requests every day. And those translates to FoundationDB queries. So what are we going to do today? We will check out the title slide. You can see that this talk is already very successful because that's already done right off the bat. We will check out the agenda. This is where we are now. Then we will have a bird's eye view of FoundationDB, and we will discuss the theoretical failure scenarios, and then we will examine actual failures. I plan to do a live demo, but later I changed my mind because, first of all, the conference wanted the slides printed, and I found it very hard to print a live demo. And second is that I can show you more this way because we won't need to wait for timeouts and stuff like that. OK, so as the bird's eye view, FoundationDB itself is a database built up from microservices. So the microservices architecture applied to a database. And it is like the Black Knight from Monty Python and the Holy Grail. And it is very well tested. It is extremely well tested. Nothing else is tested like this. So FoundationDB has this thing called simulation testing. And this is the reason for its resilience. This would be simulation testing itself, and how impressive it is would be a totally separate talk. But Silvana is here. If you are curious more about simulation testing, you should talk to her later. So this and its good architectural choices give it extreme resilience and dependability. OK, in a nutshell, it's an ordered key value store, an ordered sharded key value store with strict serializability. And the strict serializability is with reads even. So typically, key value stores are not consistent. This is consistent. This is the highest level of consistency. And it can do also range queries. So that is an important part. So with the microservices architecture, it has the separation of responsibilities. We will talk about a few components of it. We won't talk a lot about a few other components of it. I tried to make this talk short, cram everything possible in 40 minutes. But I could easily do a 4-hour-long version of this talk. So if something is missing, you can find me afterwards. And it has some limitations. And the limitations are something to embrace. So it has 5 seconds maximum transaction time. It's not configurable. After 5 seconds, your transaction is over. There is a lot of assumptions based on this in the engine, and this is why also its recovery times are so fast. The maximum size of a key can be 10K. The maximum size of a value can be 100K. There is, again, no setting. You cannot change this. It is what it is. At the engine level, there is a lot of assumptions based on this. It has single-threaded processes. So a FoundationDB cluster is built from a lot of processes. On a modern machine, you would run a lot of FoundationDB processes. And you can get performance with parallelism. So if your client workload is single-threaded, which is very much not the case these days, and it was very much not the case even 10 years ago, and complex multi-data center application is possible with FoundationDB, but we are not using it like that. So because of these limitations, there are a couple of non-existing problems in FoundationDB that exists in other databases. Who had a bad query running on the database? Like a developer pushed out a bad SQL, then you had an outage. Yeah. So because of the limitations, bad queries are impossible, because after 5 seconds, your transaction will be killed. And that's it. You cannot have, you don't have, similarly, the jumbo chunk problem in MongoDB, right? Because the values are contained. You cannot have long transactions, and because you cannot have long transactions, you cannot have long values, you cannot have vacuum and undo issues. So it's a nice, so these seem to be limiting for a small application. It would be very limiting for, I don't know, a hairdresser appointment application, but these limitations actually help you at scale. And these limitations actually help us at scale as well. So because it's, it's microservices architecture, it is sensitive to latency, and a lot of its logic is on the client side. So the client itself is talking to every FoundationDB process in the cluster. The cluster file, which has kind of a connection string, is just an entry point. It knows all the processes, and it talks all the processes to it. The implications of this, that in Kubernetes, with multi-Kubernetes clusters, you will have a hard time with networking, but it's not impossible to do, because the pods themselves need to be accessible, which is very much an anti-pattern in Kubernetes. Okay, so again, complex topologies are supported. In these examples, I am using the simplest possible replication called double replication. The name says it all. You have 2 copies of the data. And at Tigris, we keep replication simple. So we are using either double or triple replication, so the simplest types. And we have our global replication layer, global asynchronous replication layer on top of FoundationDB. I don't want to talk too much about Tigris, but at the end, if you are curious about it, I will be around. Okay, it has a very nice Kubernetes operator. We are running it in production. It has an awesome kubectl plugin, so you have a nice command line interface to manage it. And the remainder of this talk is about FoundationDB in Kubernetes, just to put this in perspective. And all the things I'm showing you is a FoundationDB cluster running on Kubernetes. I put some output here of the kubectl plugin, like this is how you verify if the cluster is OK. So basically, you do kubectl fdb something something, and that's how you manage your cluster. It's very intuitive, very good command line plugin. OK, on failure, we have healing at the operator level. So if the operator is up, but FoundationDB has issues, the operator will try to fix it. FoundationDB itself will try to fix itself. So even if the operator cannot fix it, FoundationDB will fix itself. And this is very important, because FoundationDB alone is capable of healing itself. The operator is not in the critical path of failure handling. So what does this mean? For example, for MySQL or PostgreSQL or something like that, or MongoDB, you need the operator to fix the issue for you, to do the failovers for you. Here you don't. but it helps if you have it. And both are very powerful. I will show you graphs later and put a shameless plug here. We have an open source FoundationDB exporter, and all the graphs you will see are produced by data that was exported by this exporter from the FoundationDB cluster. Okay, let's see how does this look. So the rectangles are storage pods, and the circles are key ranges. Key ranges you can imagine like, from ID 1 to 5, but these are really byte values, okay? So for example, you can see that we have 3 copies of the red key range, we have 3 copies of the yellow key range, we have 3 copies of the blue key range, yada, 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 yada. And it is distributed like this. The storage processes, the storage pods are not copies of each other, okay? But we will have 3 copies of every different key range, okay? What if this fails? So I made it like a nice animation. So if this fails, we lose a light blue and a dark blue key range. We make an additional copy of both the dark blue and the light blue. So redundancy is restored, even if I never, ever replace this process. We went to 15 processes, from 15 processes to 14. We have healthy replication again, okay? Then comes the operator. The operator will restart the process, and we will have an empty processes, and the process and the data will be here, and FoundationDB can place new data on this process. Except if we can get back the volume, we might get back the data as well. We will see examples for both, but this is it in a nutshell. Why is this so great? On failure, I need to copy a set of key ranges, and these copy are not one-to-one, but many-to-many operations. If I have 1 terabyte of data going out from a 10-process cluster, in traditional databases, I need to make that copy of 1 terabyte from one machine to another, even with MongoDB, in a MongoDB replica set. Here, I need to make that 1 terabyte copy between all the machines in the cluster. So because it's many-to-many, these copies are extremely fast, and the time to recover is also very fast. Okay, how does it work with log failure? So logs are separate processes in this database. This is the transaction logs or the val logs in Postgres terminology, or the InnoDB transaction logs in MySQL terminology. And each storage process has a primary log process that has all the changes that storage process needs. And if that fails, the storage process needs to assemble the stream of changes from every other log process in the cluster. So all the logs know about all changes, but all the logs, they don't contain all the changes. How actually it's done, some of the logs will have empty changes. So not all the logs will have the data for the change, but all of them will know about the version. Okay. And in order to make this talk contained, I won't talk much about the failure of the stateless components, because you can imagine that replacing a stateless component is like you start a new one, that's it. And these can have specific roles, like the GRV proxy is the one that determines that hands out read versions. So that is the component that determines the order. We have a component for conflict resolution. We have a component for rate keeping, and so on and so forth. So how does it behave? I conducted some tests. I was lucky because when I made this talk, we were just building out a new data center, so I just grabbed 8 Kubernetes workers from it and created a test cluster on it. It's 3763 with Redwood storage engine. This is kind of the state of the art. So if you create a new FoundationDB cluster, you should use 3.7 and you should use Redwood. Redwood is the LSM, the log structure itself, the LSM storage engine for it. And in the cluster, I had 72 storage processes, so 9 per physical machine, 16 stateless, and 12 logs. This is a not too large, not too small cluster, more on the smaller side. But it's good to, it's large enough for me to show you everything, and it was small enough so the things I will show you didn't take ages to make. Okay, what client did I use? I used Go YCSB with the FoundationDB benchmark. So we have 48 client pods running with 32 threads each. So we have a lot of clients. We have 100 byte key fields and 1K value fields. And I generated total of half a terabyte test data, which is 1 terabyte replicated size, which FoundationDB has some overhead, so that ended up using 1.3 terabyte on disk. So when you calculate with the total size of a FoundationDB cluster, you need to take replication into account plus some overhead. Not a full copy, but almost. Okay. So let's examine what happens with a single storage pod failure when the operator is running. So I issued that command, k delete pod that -- force. The pod was recreated by the operator, the exact same pod. And this is what we saw. So in this graph, you have available as the green and healthy as the yellow line. So for one sample, healthy went to 0, while the operator fixed the pod rejoined, and the cluster went back to healthy. There was no data copy triggered during this. So this is the data movement. So because the pod came up with its volume, there was no need to copy any data to recover from this failure. Okay. So how about more than one storage failure? So let's kill all of them in a loop, because why not, right? So originally I made the cartoon Black Knights use the limbs, but I didn't want it to be very violent. So instead the Black Knights are falling and coming back up. So this is how it looks like. Every minute we kill a pod, and the operator recovers. Things are fine. Let's be more brutal. Let's kill pods faster. So in this case, we have lots of falling Black Knights, but few standing. So what happens in this case is that before we manage to bring the pod back, by the time we manage to bring a pod back, another one fails. So the cluster is constantly in unhealthy state. It might recover for some brief periods of time, but we had no data copy, we have no availability issues. And you might wonder, what's the performance during all this? That I killed storage pods in a loop. And this is the QPS graph of it. So at the beginning, the benchmark was set to do around 50,000 QPS, and this is update workload. So practically reading the key and updating its value to something else. So at the beginning, this was not noticeable at all, single storage pods. And when we started to become more and more aggressive, yes, you see a bit of a performance drop, but it is available and you can use it. And as soon as it was over, performance went back to normal. This kind of recovery time is not normal for other databases. If we kill its storage is this fast. But I didn't stop there. So let's kill all storages without sleep, right? What can go wrong? So this is like every single storage process in the cluster goes down within a few seconds. So how does it handle that, right? We will see if it really deserves the title of the Black Knight. And it does. So now we are killing the storage pods fast enough to finally make the cluster unavailable, okay? By just killing everything in a loop. But we cannot be happy for long, because within a minute it became available again, because the storage pods were restarted by the operator, they rejoined the cluster. And we achieved one more thing, that the storage pods that rejoined the cluster started restoring redundancy. So we kicked off some data copy. Like this is around tens of gigabytes in a half a terabyte cluster. But soon it realized that the data copy is not actually needed, so it canceled it because the rest of the storage pods came back up. And also you can see on the performance, we had an issue for a minute or so, and then we are back in business. And again, this is killing every single storage pod that the cluster is made up of. Every single one of them. And it stands up like, whoop. OK, so now let's talk about the other stateful components, log failures. OK, so logs are the ones that are taking in the changes from the users, and all logs need to know about all versions. Version is a similar thing in FoundationDB than as a sequence number or a log sequence number in other databases. And more logs does not necessarily translate for more write performance than that, so there is like an optimal number of log pods. OK, let's examine similarly the single log failure with the operator running. Then, because all logs need to know about all failures, this is actually an availability dip for a brief period of time, actually for 5 seconds to be exact, because the transaction time is 5 seconds. After that, the cluster realizes that the log is gone, or the operator restarts the log pod, and we move on with life. OK, so same thing, multiple log failures with the operator. So same nice black knight, only one falling, only one standing. So we kill them one by the minute. And what we see is very similar to the storage pods in terms of availability, that the cluster goes to not available. But we also see the performance touching, the workload touching 0 for brief periods of time. So a log failure translates to a stall in the cluster, a 5-second stall. OK, but let's not stop there. Let's do all logs down similarly. So again, while writing at 50,000 QPS, we kill off the component totally which absorbs the changes. What can go wrong, right? So in most databases, this is a catastrophic failure, and you need to do instance recovery and stuff like that. This is what happens with FoundationDB. It indeed becomes unavailable for roughly 3 minutes. Then the operator restarts the pod, and it keeps going as if nothing has happened. So this is like awesome. It's very different to operate this than to operate anything else. I can tell you that. I'm doing it for 3 years. OK, let's examine the things without the operator. So why do we want to do this? Because do I kill the operator regularly in production, or why is this interesting? No. It's interesting because even if you have the operator, you can have circumstances when your pods cannot come back up. For example, a rack fails or something like that, right? So now the operator won't replace anything. We leave it all up to the FoundationDB itself. And in production, this happens with rack down, availability zone down, things like that, okay? So what happens if I kill a single storage pod now? The healthy dip will be wider, and we are triggering a data copy. So we are copying the data that was residing on that storage pod to the others. And we have a bit of a dip while the copy is actually done. OK, there is a concept of zones in FoundationDB. So each storage process and each log process can have a zone. This can be an arbitrary string. And what FoundationDB does is it guarantees that the replicas of the data will be on different zones. So what do we set this to? Rack, different PDU, different building, different availability zone, something like that. Okay, so this is how you contain the fault domains. Here I set the zone to the Kubernetes worker hostname. So I can kill all the storage pods that are running on the same physical machine, and it can recover from it. So 9 pods die at the same time, full physical machine is lost, 100 gig of copy is kicked off. It is done in pretty much 3 minutes. Why is it so fast? Because it's many to many. Every other pod in the system can give the data to every other pod. And it restores redundancy like that. And then it becomes healthy again. Life goes on. We have 72 minus 9, so 63 remaining storage processes in the cluster. And it's up, and it fixed itself. OK, so in the test setup, we have 8 zones, double replication. So 6 can fail if it fails slowly enough. What does slowly enough mean? Slowly enough means that we have time to copy the data over to the rest of the pods. Okay. So for the fun of it, I made other zone failures. And you can see that as we have less and less zone, the copy process will take more and more data will need to be copied. So the height of the kicked off copy jobs will be more because we need to copy more data, simply because the zone will have more data because there is less zone. And the copy will also take longer as we kill the zones because we have less and less pods in the system, so the many-to-many effect is less and less visible. So with this test, this actually took a while. This took like almost 2 hours. So with this test, I killed zones one by one, and FoundationDB recovered itself. If I would start the operator at this point, it will recover all the lost storage pods, and then it will eventually rebalance itself, or you can do a rebuild, and it's done. So one of the takeaways is that if you want to have awesome recovery times for your cluster needs to be big enough. You need to have enough processes to handle these data copies. OK. Let's examine log failure without the operator. It's pretty much the same as with the operator, the single one, because the only thing that is different is that we don't replace it immediately. So after this failure, there will be one less log process in the cluster, and that's it. We will have less logging capacity. OK, so multiple log failures. What happens if we do multiple log failures without the operator? If it's slow enough, it has more or less the same effect as with the operator. But if we do it too fast, the cluster will be down because we break the replication rule for the logs. So this is like, at this point, I started the same killing process, and after the first 2-3 pods were killed, database was down. Again, if I started the operator up at this point, it would have recovered the log processes, and then the cluster would have moved on. I would like to have a few more words about backups and disaster recovery. So the backups are something else. It's logical backups, and they are called continuous or streaming backups. They are going to an object store. Unfortunately, we can't use Tigris for FoundationDB backups because it would be a chicken and the egg problem. But so what it does is you set it up. You set up a snapshot interval. Like I want my full backups every day, every 24 hours. And it streams the full key ranges and the changes in a way that you always have a 24-hour old snapshot. Okay, so, and once it's done, it is continuously streaming. So we have a metric in the production system called backup lag, that how much the backup, the data in the object storage is actually behind compared to the cluster. And you can get this down to less than a minute. So you can have backup on object storage that is always less than a minute behind this. Okay, the exact same mechanics, streaming changes and sending snapshots gradually, can be used for disaster recovery. And FoundationDB itself has disaster recovery utility. The only difference is that the source is a FoundationDB database, and the target, in case of the backup, is the object storage. In case of DR, the target is another FoundationDB cluster. Okay, the difficulty here is that the DR utility needs to talk to both FoundationDB clusters. Again, the client needs to talk to every process in the cluster, so it needs to talk to both of them, and typically they are in different Kubernetes clusters, so you need a way to expose the pods. And the direction switching of replication is built in, and it can switch the replication direction between your DR cluster and your normal one within a few seconds. So DR switch is also kind of, it's built in and it's great. With the traditional databases you need to build, I built countless DR, DR infrastructure, and it's here it's built in. So that's it. And with Tigris, we are using FoundationDB in a way that we have our own global application on top. So Tigris is actually backed by multiple Black Knights. And thanks, Tigris, for sending me here. And if you want to try Tigris, you can go to storage.new. I could have been fancy and put a QR code here, but it's so short, so that I just didn't bother. And we have some time for questions. Yeah?
So the general architecture, it seems to be, it's a transaction logging system, and then it just chucks any particular records that are a little bit too large to be inlined with the logs into the storage pods. Is my assumption there correct?
Yes, so the question was that the architecture seems to be that it just chunks two big transactions at the log level. Yeah, no, it's your job to chunk. It has the 5-second limit, and it has the value limit. It doesn't chunk, you chunk. And in our case, the Tigris application chunks. And that's why, that's why it is. So for example, for the recovery times, the 5 seconds transaction time, so how it works at the storage level is that in a traditional database, you would need to do an instance recovery on failure. You need to roll forward the database using the redo logs and roll back using the undo afterwards. How it works in FoundationDB is that the storages don't have recovery capabilities, and that's why it's so fast, because they keep the last 5 seconds worth of changes in memory and only flush afterwards. So on failure, the last 5 seconds are in the log, the rest is in the storage. But it's your job to chunk. The engine doesn't chunk, it's you. And you also need to write your own indexes. So this is a key value store. So you need to encode your data, write your own indexes, do your own chunking. But like I said, it helps you at scale.